You ever wonder how a machine can look at, say, 1,000 different pictures of a cat and figure out what a cat really is? I don't mean just the pixels, but the idea of a cat. It's a huge question in AI, and today we're going to pull back the curtain on a really cool tool for the job, the autoencoder.
So, right, how do we teach a machine to find the essence of an image, or really any kind of complicated data? It's not about memorizing every single detail. That would be useless. It's about finding the deep, underlying patterns, the most important features that really define what you're looking at. And that, right there, is the exact problem autoencoders were born to solve.
Okay, so here's the official definition, but let's not get scared by the jargon. It's an unsupervised neural network. All unsupervised means is that it learns by itself. You don't have to sit there and label millions of images telling it this is a cat, this is a dog. It figures out the patterns on its own. And its whole job, its entire reason for being, is a two-step process. First, it squishes the data down into a super compressed version. That's called encoding. Then, it tries to build the original data back up from that tiny version, and that's called decoding.
To really get a handle on this, here's our game plan. We'll start with the basic blueprint, the simplest version. Then, we'll see how to add some clever rules to make them smarter. We'll even see how they can learn from messy, imperfect data. We'll touch on some more advanced models, and then we'll wrap it all up so you've got a great mental toolkit to work with.
All right, let's dive right in with the most fundamental version. People often call it the vanilla or undercomplete autoencoder, and trust me, if you can really get your head around this simple one, everything else we talk about is going to click right into place.
So take a look at this diagram. It's actually pretty elegant in its simplicity. Over here on the left, that's your input data. Could be an image, whatever. That data gets fed into the first part, the encoder. Its only job is to squish everything down into this tiny middle layer. We call that the bottleneck for obvious reasons. Then the second half, the decoder, has the exact opposite job. It takes that tiny compressed code and does its best to rebuild the original data on the other side.
The whole process really just boils down to these three steps. Step 1, encode. We take our data and squeeze it into that small, dense representation. Step 2, decode. We take that compressed code and try to blow it back up to its original size. And step 3, this is the magic part, compare. The network looks at the original and the new one it just made and asks, how different are they? That difference is the reconstruction error. It's basically a score for how badly it messed up, and its entire goal in life is to get that score as close to 0 as possible. That's the learning process right there.
This leads us to the most straightforward type we mentioned, the undercomplete autoencoder. The name totally gives it away. The hidden layer is smaller, or undercomplete, compared to the input. Think about it. This physical bottleneck is an incredibly powerful constraint. It's like trying to explain a whole movie through a single text message. You can't just copy every detail. You are forced to figure out the most important plot points and leave all the extra stuff out. That's exactly what this network does.
Okay, cool theory, but what can you actually do with this stuff? Well, a ton, actually. The most obvious one is data compression, literally making files smaller, like zipping them. It's also amazing for feature extraction, which is just finding the most important signals in your data to help another model make better predictions. And my personal favorite is anomaly detection. This is super clever. If you train a model on thousands of normal transactions and then a fraudulent one comes along, the model will do a terrible job reconstructing it. That failure is your red flag.
So, we've seen how a physical bottleneck works. It's simple and effective. But what if we wanted to get a little more creative? What if we could use clever rules to guide the learning, instead of just relying on the architecture? Well, that's what we're diving into next.
Now you might be thinking, hang on a second. If the small bottleneck is so important, what happens if we make the hidden layer bigger than the input? And that is a fantastic question, because you're right, that could be a huge problem. Without any other rules in place, the network would just get lazy. It would just learn to be a very expensive copy machine, passing the data straight through and learning absolutely nothing useful. So, how do we stop that?
The answer is the sparse autoencoder. You can have a big hidden layer, but you add a special rule. It's called a sparsity constraint. Think of it like this. You have a huge team of employees, those are your neurons, but there's a rule that for any given task, only a small handful of people are allowed to work on it. The network gets penalized if too many neurons activate at once. This forces different neurons to specialize. One little group might become experts at detecting eyes, another at noses, and so on. No more lazy copy-pasting.
Okay, so making only a few neurons work at a time is one way to add a smart rule. But here's a completely different and equally powerful idea.
What if we told the network, hey, I want you to learn the big picture, and I want you to be so good at it that tiny, insignificant changes in the input don't throw you off at all. In other words, we want to force it to be robust. And that is the whole idea behind the contractive autoencoder. Now I know, we're looking at some math, but don't panic. It's simpler than it looks. That L is the loss function. It's just the network's how badly did I mess up score. The top one is the standard one we've been talking about. It only cares about how good the reconstruction is. But look at the bottom one. It has that original part plus a whole new penalty term. This new term is the secret sauce that makes it robust.
So let's pull that new part of the formula apart. First, you've got lambda. Just think of that as a volume knob. It controls how much we care about this new penalty versus the original reconstruction error. Next is that funky dH/dx. That's the Jacobian matrix. All that really means is it measures how much the encoded stuff changes when the input stuff changes just a little bit. And finally, those double bars. That's the Frobenius norm. It's just a way to get a single number that represents the overall size of that change. And the whole point is to force that number to be as small as possible.
Okay, Frobenius norm sounds super intimidating, but let's actually calculate one. It's really just simple arithmetic. Say this is our matrix. Step 1, you just square every single number inside it. So 1 squared is 1, 2 squared is 4, 3 squared is 9, and 4 squared is 16. Easy enough. Step 2, add them all up. 1 plus 4 plus 9 plus 16, that gives us 30. And the final step, just take the square root of that sum. Boom, that's the Frobenius norm. By telling the network to keep this number small, we're basically telling it, hey, don't overreact to tiny little changes in the input.
Now for what I think is one of the cleverest twists in this whole story. Up until now, we've assumed we're feeding our models perfect, clean data. But what if? What if the secret to learning better was to actually train it on bad, messy data on purpose? This is the wild idea behind the Denoising Autoencoder.
So check this out. The whole goal changes. It's not about reconstructing the exact input it was given anymore. Its goal is to take a damaged input and reconstruct the original clean version. It's like I give you a smudged, blurry photo and ask you to draw what the person originally looked like. You can't just trace it. You have to understand the underlying structure of a face to fill in the missing pieces. That's what we're forcing the network to do here, to learn the real patterns so it can fix the damage.
So the training process gets a little twist. Step 1, we take a perfectly good input and we mess it up. We add some noise, we corrupt it. Steps 2 and 3 are the same as before. We encode and then decode that new noisy version. But step 4, and this is the absolute key to the whole thing, when we compare the output, we don't compare it to the noisy thing we put in. We compare it to the original pristine input. That's the secret. That's what teaches it how to become a denoiser.
And you can probably guess where this is useful, right? I mean, image denoising is the classic example, taking old, grainy photographs and making them look sharp and clean. But you can apply the same idea to cleaning up static from an audio recording or filtering out junk from sensor data. It's a super practical and powerful tool to have.
All right, we've got the fundamentals down pat. We've built a solid foundation. Now, let's just briefly look at a couple of more advanced models that take these core ideas and really push the boundaries of what's possible.
First up is the convolutional autoencoder. This is the one you want to use for images, full stop. It uses special convolutional layers that are designed to see visual patterns like edges, corners, and textures, kind of the same way our own brain's visual cortex works. They just have a much better intuition for pictures. Then you have the variational autoencoder, or VAE, and this one is a whole different beast. Instead of learning a single fixed code for an image, it learns a probabilistic recipe for how to make that image. And that's a game changer because it allows the VAE to actually generate brand new, completely realistic data that's never been seen before.
Whew, okay, that was a lot. But we've gone from the absolute basics all the way to some pretty advanced stuff. The best way to think about everything we've talked about is like having a toolkit. You know, you wouldn't use a hammer to turn a screw, right? It's the same idea here. Each autoencoder is a specific tool for a specific job.
And this table right here is your cheat sheet. If you need simple data compression, you grab the vanilla autoencoder. If you need to find the most important features in a huge data set, the sparse one is your friend. Want something really robust that isn't fooled by noise? Go contractive. Need to literally clean up messy data? That's a job for the denoising model. And if you want to get creative and generate brand new things, you'll want the variational autoencoder. It really is all about picking the right tool for your specific problem.
So, at the end of the day, autoencoders are all about one thing: finding that essential, hidden structure inside complex data. They're like a key for unlocking the core patterns that we could never see on our own. Which really just leaves one final question to think about. Now that you have these blueprints, what hidden patterns will you uncover?